Oh, hi. I'm Kaushik Roy. I'm a professor of electrical and computer engineering at Purdue University. And today I'm going to be talking about neuromorphic computing. In particular, actually talk about neuromorphic systems going all the way from algorithms down to circuits and hardware architecture. Now, we all know that the AI revolution started back in 2012 or so. And that really happened because of the convergence of availability of data, algorithms, and also the GPUs or the hardware architecture. And since then, magic has happened. Deep learning, if you open up any tech news today, you find different kinds of milestones, and some of those are quite interesting to the effect that, in one case, as you can see, in a CNN Business News, it came out that AI won an art contest, and the human artists are furious. So what it really tells you is that it's really made great strides in the recent past. However, if I were to really look at biological systems, the biological systems, despite this tremendous progress, they're still much, much better than the artificial systems of today. So if you are to really try to do some comparison, and that's what we did, we considered the reactive behavior of a fruit fly. Now, it turns out that the fruit fly has about 100,000 neurons or so, and these flies, with those 100,000 neurons, they can fly really fast, avoiding obstacles, dodge dynamic objects, and so on. So to that effect, what we tried to do in one of the projects, and I'll talk about that later on, is try to build something which can try to mimic the activities of the fly. Of course, we couldn't really do what it does, but we implemented it in one of our collaborators at UPenn did what's called a flying monkey. And it turns out that the compute power of that flying monkey was about 1 to 2 watts. Whereas now if I try to compare that with the fruit fly, the compute power of the fruit fly is about microwatts or so. So there's a huge difference, as you can see. Now, if we look at further details and go up the chain, going from fruit fly to, let's say, a mouse or a dog, all these animals, they do their brain power is possibly going to be of the order about milliwatts to watts, or half a watt or so in case of a dog. Whereas if I look at the corresponding Boston Dynamics, Spot robot as an example, that's about 15 watts of compute power. And then the humans, it's quite widely thought that the power consumption of the brain is of the order about 20 to 30 watts. Whereas, if I were to really look at, mimicking some of these activities, for example, playing the game of Go, and that would require about, 10 to the 6 watts of, compute power. So there's a humongous difference between the biological systems and the artificial systems, even though we might have made a lot of progress. So what we did is we did an analysis of the efficiency gap and did a case study on object recognition in a smart glass with a state-of-the-art accelerator. In this particular case, what I'm really showing is a Google Edge TPU, where in this particular example, one can wear that smart glass to recognize, for example, objects. And in this particular case, what we did is we implemented a RetinaNet DNN on a smart glass and wanted to figure out, hey, how much the power consumption, the energy consumption is going to be. So without going into the details of the analysis, what we found out is under ideal conditions, the battery life is going to be about, an hour, 64 minutes or so. And that's ideal condition. But if you now consider, for example, display powers and all, turns out that it's going to go down to probably half an hour or so. So that's not sustainable. And on the other side of it, we also have an existential proof that the brain is reasonably efficient, right? So the question then, of course, is where are these inefficiencies coming from? So it turns out these inefficiencies are coming from not knowing exact algorithms that's there in the brain. The hardware architecture of the brain certainly doesn't look like the standard von Neumann architecture. We don't have memory on one side of the brain and the compute on the other side. They're all mingled together into one system where the computations are done somewhat in the memory itself in an efficient way, which we don't exactly understand well. And finally, at the end of it, the devices that mimic the neurons and synapses. Today we use CMOS technology, which is the workhorse of all digital systems of today. However, they may not be able to very efficiently mimic the neuronal and the synaptic activities. So to that effect, there's a need to rethink the kind of devices that one should use for mimicking some of these neuronal and synaptic activities.